Hi guys, so this is our PIC video assignment from group C3, and starting off with question 1. So you can either pause the video or just take a screenshot of it. And yeah, so question 1 tells us that the system consists of a series drum which stores gases, and in the inlet is the molar flow rate Qi, and the outlet is Q. You can see that at the outlet there's a control valve, which tells us that Q will be the manipulated variable. So we've got to make assumptions for everything, for every modeling questions that we do, right? So the first assumption is that the gases behave similar to ideal gas. The next assumption is that the system is isothermal, meaning that the temperature is constant. And the other assumption is that there is constant holdup in the system, meaning that the volume is constant. Okay, so now let's do the total mass balance. And if you can recall from the question, it tells us that the inlet and outlet are in molar flow rates, but we want it in mass. So we've got to somehow change it to mass. So we're doing dmn over dt, where m is the molecular mass and the n is the moles. So when we put it in the forms of the units, we can cancel out the kg over mole for the m, and we just times it by the n, which is in moles, which will give us kg. So that's settled. And just cross out the m because, yeah, it's constant. So we've assumed that it's an ideal gas, so we can use the ideal gas law, which is PV equals to nRT, and we just want it in terms of n, so n equals to PV over RT, so that we could substitute it into the dn over dt equals to Qi minus Q. So now we just substitute n equals to PV over RT, and that will give us d bracket PV over RT over dt equals to Qi minus Q. And we want it in terms of dp over dt, since p is the variable that we can control. So just flip over the v over rt, which will get rt over v times Qi minus Q. And therefore our dynamic model of the system is dp over dt equals to RT over V times Qi minus Q. Alright, now we can find the process variables. And for this question, there are only 3, which are P, Qi, and Q. And the input variables, there are 2 types, which are manipulated variable, which is Q, since there was a control valve at the outlet, and disturbance variable, which is Qi. And for output variable, there's only one, which is the control variable, and we've determined that the variable that we can control is the P. And the constants that we have here is the volume, temperature, and the gas constant. So now we just simply find the steady state equation, and how to find it is that we just make dp over dt equals to 0, so that will leave us with 0 equals to RT over V times Qi bar minus Q bar, and we just bring the RT over V to the left hand side, and Qi minus Q bar both, since those 2 variables are the ones that we cannot control. And lastly, we just need to find the degrees of freedom. We only have one equation, so equation equals to 1, variables equals to 3, and degrees of freedom equals to 3 minus 1, which is variables minus 1. And since our disturbance variable is determined by the surroundings, we have 2, and manipulated variable, which is only 1, is specified with the controller. It is exactly specified.
Good day, I am Ho Chit Seng, and today I will be discussing the question 3 of the video exercise. So the question given that we have a CSTR liquid system with a heating coil in it and some properties. Thus, in the question, it is given that the density is constant at 800 kg per meter cubic, and the CP, which is heat specific heat capacity, also given 0.5 kilocalorie per kilogram dot degree Celsius, and the mass flow rate in is 25,000 kilogram per hour. It is taken to be the steady state value as it is not mentioned to be constant. And then it is also given the constant hold up, which means the constant volume. So given the mass in the question and having the density, we can get the value from V equal to mass over density. And then the inlet temperature given at 30 degrees Celsius, again taken as steady state value due to no mention of constant. The inlet steam temperature into the heating coil is at 150 degrees Celsius, and the steady state temperature in the tank is 90 degrees Celsius. Again taken at steady state due to no mention of it being constant. So moving on to the assumptions. So since it is a constant hold-up system, we can assume it is constant volume. And then we assume it is constant Cp because this is a liquid system. And then we also assume perfect mixing due to it being a CSTR. Thus the temperature at the outlet should be same as temperature in the tank, and we use the symbol T to designate it. And the internal energy U will be can be approximated by the enthalpy H. Okay, let's move on. For the mass balance, we will start with d rho v per dt equal to Wi minus W. So since the density is constant, it can be taken out. So we get the rho dv dt below. Take note that because it is a constant hold up with constant volume, so the dv dt will be 0. Thus cancelling it, we will get Wi equal to W. Let's see the energy balance. So for the energy balance, as we can see here, we start with du dt equal to Wi hi minus wh plus q. And since u can be approximated by h, and h is mcp delta t, m is expanded to rho v, and delta t is t minus t ref. While hi, the specific enthalpy is just the enthalpy divided by the mass. So we just don't have the rho v component. And since there is the I subscript, so we have the I subscript for the t there, ti. While for the h is just t instead of ti. And we also know that the wi same as w, so we can factorize to the term together as shown below. So we just change all the term there with the one we found out. And then since the ti minus t ref there, since the t ref can be cancelled, we cancel it. And the rho v cp is constant, so it can be taken out. And then by removing the term to the denominator of the other side, finally we get w over rho v ti minus t plus q over rho v cp. Moving on. Just now we already got the dynamic equation. Now we want to find the steady state equation. So for the steady state equation, we just evaluate everything at steady state. So dt per dt become dt bar per dt, which is actually equal to 0. And then equal to w bar ti minus t over rho v plus q bar over rho v cp. So next we want to linearize these terms. So for the non-linear term, we have wti and wt. So we have the function of wti, which is wti over rho v. The second one is the function of w bar, ti bar. So we just change w and ti to its bar form, a steady state form. Then we have df per dw evaluated at w bar, ti bar. So differentiating it, we have ti over rho v. And then the ti become ti bar since it is evaluated at w bar, ti bar. Same for the df dti, we get w bar per rho v. I forgot to mention, but let's take the steady state equation just now as equation 1. So now let's move on to see the linearization. So we have the Taylor series first order expansion, in which we for two terms, which is fx1 x2 equal to fx1 bar x2 bar plus we have dx1 evaluate x1 bar x2 bar x minus x1 bar plus df per dx2 evaluated at x1 bar x2 bar x2 minus x2 bar. So from the function just now, we just sub everything and then we will get this wti over rho v equal w bar ti bar over rho v plus ti bar over rho v w minus w bar plus w bar over rho v ti minus ti bar. And then since wt per rho v is just difference of ti and t, it should have the same integral, etc. So just instead of ti, we have the t. And then now we just sub back it into the dynamic equation and simplify. So we will have dt per dt equal to ti minus t over rho v w minus w bar plus w bar over rho v bracket ti minus ti bar minus bracket t minus t bar cross bracket plus q over rho v cp, which we take as equation 2. So after getting the equation 2, we can find a deviation variable, which is just this equation 2 minus equation 1, or the dynamic equation minus the steady state equation as shown. So here you can see that the ti bar minus t bar, the part up to q over rho v cp, is from the dynamic equation, while the rest, which is the minus w bar bracket ti bar minus t bar over rho v plus q bar over rho v cp, comes from the steady state equation. Thus, if we say that t prime is t minus t bar, ti prime is ti minus ti bar, w prime is w minus w bar, and q prime equal to q minus q bar, we'll have the equation dt prime per dt equal ti bar minus t bar over rho v w prime plus w bar over rho v ti prime minus t plus q prime over rho v cp minus w bar over rho v ti bar minus t bar. So next we want to do the Laplace transform, but few things take note is the Laplace of a df dt is as fs minus f0, but f0 is always 0 for deviation variable, which is true for our case. So we just have as fs since this is deviation variable, and L of f of t is just f of s. So continuation from just now, Laplace of a constant a is just a times 1 over s or a over s. So by using the Laplace transform, we will get sts equal to w bar over rho v ti bar minus t bar times 1 over s plus w prime s ti bar minus t bar over rho v plus w bar over rho v ti prime s minus t prime s plus q prime s over rho v cp. So that here we just move the s from the left side to the denominator. So we see 1 over s become 1 over s squared, and those that don't have 1 over s initially get the 1 over s. So some notes on the Laplace inverse. Laplace inverse of a over s squared, we will just get a t, and Laplace inverse of f of s over s, we will get the integral of 0 to t ft dt. Thus by using it, we will get ts equal to w bar over rho v ti bar minus t bar times t plus ti bar minus t bar over rho v integral from 0 to t w prime t dt plus w bar over rho v integral 0 to t ti prime t dt minus integral 0 to t t prime t dt plus 1 over rho v cp integral 0 to t q prime t dt. Since we are not sure of the function which is w prime t, ti prime t, t prime t, and q prime t, so we cannot change it, integrate it. So we can do is just substitute the value given in the question. So we get finally ts is negative 9375 over 13 minus 3 over 104 equal 0 to t w prime t dt plus 625 over 52 integral 0 to t ti prime t dt minus integral 0 to t t prime t dt plus 1 over 1040 integral 0 to t q prime t dt. So that is all. Thank you.